Okay, so welcome to the week 6 of problem solving session for the computational complexity course. And today, the topics for today would be the randomized classes BPP, RP, ZPP, and we'll um, look at some simple problems on circuits. Okay, so so recall that the RP class that we defined was that um, you say L is in RP if there is a deterministic machine M or decider M such that if X is in the language, then M accepts is with good probability, and I'll half plus epsilon, and if X is not in the language, then M rejects with a good probability. Okay, so sorry, I'm sorry. So M always rejects. Okay, so one thing to note here is that in this case, it always makes error when it never makes error when X is not in the language. So the only chance of it making an error is when X is in the language, and we know that with good enough probability, it will give correct answer. So we can define a similar notion where like we had NP and co-NP. You can say that L bar is in co-RP whenever L is in RP. Okay, so the both the definitions have one thing in common, that in one case you can always trust the answer. In the other case, you have some guarantee. So these are called one-sided error algorithms, and we don't know whether RP is equal to co-RP, so this is an open problem. And the other thing is that you saw some examples, natural examples of languages in this class. For example, polynomial identity testing. This is in co-RP. So the picture currently is like this. So you have RP here, then you have co-RP. Okay, and uh, this intersection that is there is what we call ZPP. So ZPP is the zero error probabilistic polynomial time. Class. And how did we define that? There are we say that if X is in the language, then okay, so there are actually two equivalent notions. So one is that X okay, so X M decides X with probability at least half, and otherwise M says don't know. So what do we mean by this? If X is in the language, it will accept. If X is not in the language, then it will reject. And this happens with a good enough probability, but it will never give you errors, in the sense that if X is in the language, it will never say reject, and vice versa. It may say don't know, but it will not give errors. The other equivalent definition that you saw is that it always answers correctly, but we are compromising on the time. Instead of deterministic polynomial time, it it is guaranteed to run in expected polynomial time. So the definition 2 that we had was um, M always gives correct answers, but the runtime is expected polynomial time. Okay, and we saw in class that these two definitions are actually equivalent. So, and you also saw that in fact the intersection of RP and co-RP is exactly equal to ZPP. And the other natural question is, instead of asking, so in RP and co-RP, both of them, we had this uh, thing that on in one case we are always correct, in the other case we have some guarantee. So natural question is, can I define a class where in both the cases we are answering correctly with some good enough probability, but say we don't have this kind of a guarantee, so we are allowing to make errors in both the cases. So this is what we call BPP class, or bounded probabilistic polynomial time. So what this means is that x is in L is in BPP if x in L implies probability that M accepts x with good enough probability, let's say 2/3 for now, and if x is not in L, then probability that M rejects x is at least 2/3. So these are the things that we saw, and clearly by definition RP um, sits inside BPP because I mean BPP is just a relaxation on this condition. So we know that RP is contained in BPP, and we also know that RP is contained in NP. So this is a very simple argument, just follows from the definition. So yeah, we know that it's contained in both of these, but we don't know the comparison between NP and BPP. So this is a big open problem, whether NP is equal to BPP. We don't know containment in either direction. Okay, so yeah, any side is open. And another question that we have is whether BPP is equal to P. Okay, so these are two big open problems, and a lot of research actually goes on in on this side. Okay, so there are this pseudo randomness and extractors and so on that are studied in the quest of this question, but we'll not get into it because it's not in the scope of the course. Yeah, so that's all about the definitions. um, okay, so if there's anything further, we will define when needed. So with that, let's get into the questions. So you want to show that this class BPP is contained in P space.
So, yeah, so because in the BPP we are, I mean, everything more or less is same, except that the errors may happen at both the sides, and additionally we would be using some random tape at the most. But then this we would be requiring a polynomial amount of the space for sure. Because the extreme thing would be that if the string is a part of the language, then it gets fully accepted. And if the string is not the part of the language, then it gets fully rejected. And here we have scope of making some errors, but it doesn't have anything to do with the space. And since NP is the element of the P space, and even though we do not know the relation between BPP and NP, but still the space-wise requirement would be that BPP is the subset of the P space.
Okay. So okay. So one thing is that on this side we have a language that is allowed to make errors. But on this side we have a language which is not allowed to make errors. So the idea is correct that we can do this in polynomial space, but we want to make sure that there are no errors that are happening.
Oh, yes, uh, that should be taken care of. Yes. So, but common sense wise also, I mean, the intuition is that we won't be requiring, I mean, more than polynomial amount of the space, even if it makes error. even if it makes errors.
If it makes
So
error, it's clear that it will not go beyond p space. In fact, it runs in polynomial time, so
uh,
it cannot touch more
but
than polynomial many cells.
but then I have another idea that
Hmm.
this RP is a subset of the BPP,
Hmm.
and moreover this ORP is also the subset of the BPP.
Hmm.
So from RP thing we are sure about not thing, and for CoRP we are sure about the yes thing.
Hmm.
Because RP is rejecting only in one side, and the other side we are sure.
Hmm.
And for CoRP, the vice in the reverse side.
Hmm.
So since both RP and CoRP are contained are there inside the BPP,
Hmm.
if we mix this RP and then CoRP, we won't be making any error as a whole collectively. Uh, and then it would require polynomial in this case, I guess.
Hmm. So what you are talking about, this intersection of RP and co-RP, this will give you the ZPP class, where, right?
Not the intersection, but then the union kind of. So if I
Mm,
take union, then also I would be sure for I mean if X is element of N and if X is not an element of N, and this RP is a subset of the NP you said,
hmm.
and so this probably this co-RP. I don't know the status of the co-RP. If RP is a subset of the NP, would it mean that co-RP is a would be the subset of the co-NP? Is this the case?
Yeah,
But
that
it would
follows
require
by definition. Yeah.
yes.
Hmm.
So in that case, but then you would be requiring in both the cases you would be requiring the polynomial in this case.
Hmm. But even if, let's say, we do union, okay, that this part, okay, there could be languages that are out there which are, uh, I mean, which are there in BPP, but not in either of them.
Yes, there could be uh there could be. So
Okay, so I'll just
yeah,
give a small hint of. So let's just look at the definition of BPP. So okay, so when we look at this probability, we are going over some random choices, some random bits that are not that don't sorry that don't depend on the input. Okay, this got stuck somewhere. Okay, I think this screen share got stuck. Okay, I'll reshare it once. Okay. Okay, so notice that we have this probability over some random bits here. Um, am I audible? I think there's some issue with my internet. Okay, okay,
yes, you are
okay,
right. Yeah.
okay. So, what this means is that if I m is here some polynomial, m is some polynomial in terms of n. So, so notice that what this really means is that if I look at um, all possible random choices here, so how many of them do we have? We have 2 to the m of them. So in two-thirds of these fractions, we are going to be correct, and in one-third of this fraction is bad for us. Okay, so if I want to simulate this thing deterministically, natural thing would be that you go through all random choices. So we're going to simulate this decider m on r for each r.
your shared
Yeah.
screen is not visible.
Oh yeah, yeah. I just realized that I'm trying to connect from the iPad again. Mm, okay. Um, is it visible
Yes,
now?
this is
Okay,
yes
okay,
visible now.
okay. So, yeah. So natural thing would be that we go through all possible hours and take the majority. Right. So
Yes.
if majority of them accept, then we will accept. Otherwise, we reject. Okay. So the only problem with this is that the number of uh, times we may have to simulate this could be exponential. I mean, in fact, it is exponential. Right.
Yes.
So, but we don't care about that. Right? All we need to argue is that this can be done in p space. It's fine if it takes exponential amount of time. So that is the trick. So these are exponential choices, but we want to only need to show p space. So yeah.
So say, because if a Turing machine which runs in the polynomial amount of the space, say Fn, may require, so there used to be one result there. So then we require 2 raised to the power of the order of Fn amount of the time. So even if we have to explore those many number of the possibilities, those possibilities can be explored in the polynomial space. Now same thing is happening here also. So even if all the possibilities, I mean all the bits generated by, I mean random bits
Hmm.
corresponds to, say, even I mean some of them are incorrect also. Then then how does it matter for the space? I mean from the space viewpoint, it's still everything can be decided on using the polynomial space only.
Yeah, yeah. So the only thing we need to show is that um, this the fact that I don't need to store all the exponential many random choices. So that's what we need to argue, that we don't really need to store all of them, 2 to the m many of them. We will just keep a counter. So keeping a counter will only require us m many bits, right? So you start from all zeros, then um, I mean go through all 2 to the m many possibilities. But you don't need to store all of them. We will just keep a counter. That's the only.
Yes, yes.
So this can clearly. So we are only storing these m bits at any given point of time. We are only storing m many of them. So this is clearly um, can be done in p space. And the other thing is that we know that the machine m runs in poly time. So the amount of space that it will end up using is polynomial, and once that is done we will know whether it accepts or not. So if it accepts, we will increment the counter here. So this is some accept counter which will store the number of times we accepted. And you don't really need to store reject counter, because at the end we will just see whether there are more than half accepts or not. So then we can reuse this space also in the second time when we increment the counter to 0 0 and so on up to 1. We will reuse this space for m, and um, and then decide whether to increment the counter or not. So this can also be done in polynomial space. This will take at most um, yeah, this will also take at most 10 bits. So altogether, we are running in p space. So that's the only, yeah, small part of the argument.
Yes.
Okay. And hmm, okay, yeah. So then we'll do the next question. So you want to show that you. Hmm,
Yes. So yeah. So BPP. So closed under. So say if a language is in BPP,
hmm,
uh, then its complement would mean that all the strings which are not the part of the I mean which are not the part of the language. I mean, if L is in BPP, then the complements of L would also be BPP in the sense that we would be observing the errors. I mean, in both the sides.
hmm,
Uh, because in the original also we are observing the errors in both the sides.
hmm,
The only thing remaining is with this quantity, it's a 2 by third.
hmm,
And this 2 by third probably is not that strict. It could
hmm,
also be, say, half also with slightly more than half and slightly less than half kind of the thing.
hmm,
Uh, so, uh, so that would for the ZPP it is straightforward because ZPP is always right. So it is. I mean, at the most in
hmm,
the case of the ZPP, it has to say more number of the nodes don't know. I don't know more times. But in the ZPP also, the machine won't be saying don't know more than 50% of the time.
hmm,
So ZPP is sure that it is closed under complementation. And as far as the BPP is concerned, so now only thing remaining is to handle this 2 by third.
hmm. Yeah. So, um, okay. So this is, so let's say L is in BPP, and if what we want is that we want if X is in L complement, then probability that M accepts is 2/3, and if X is not in L complement, then the probability that M accepts X is, sorry, M rejects X is at least 2/3. This is what we want.
Yes, and then for the original BPP, if X is the element of the language, then the probability of because if X in the original language, say if if X is the element of the complement of L, it would mean that X is not the element of L. So
Hmm.
if X is not the element of L, then the probability of rejecting the string X should be greater than 2/3.
Hmm.
So if probability of rejecting is greater than 2/3,
Hmm.
then in the complement, I mean, we can uh, construct a machine that would accept this
Hmm.
string with the probability 2/3. We
Hmm.
can do some swapping kind of the thing probably. That whenever one machine, I mean, accept with the probability greater than 2/3,
Hmm.
the other would reject it with the probability, say, with the same probability,
Exactly.
if that can be done.
Yeah, yeah, exactly. That is, yeah, that's the one. So, we will construct a machine M prime for L complement. So, what it does is it runs M on X, and if M accepts, then we reject, and if M rejects, then we accept. So, this is the only change. We are just flipping the acceptance. So, what will happen is that when M, okay, let's say X is in L complement, then probability that the original machine M, okay, this is same as X is not in L. So what this means is that probability that original machine M rejects X is at least 2/3, right? So
Yes,
yeah, so
yes.
what this means is that probability that a new machine M prime accepts X is at least 2/3, because we only flipped the acceptance rejectance. So this gives us the first requirement, that when X is in L bar, we are going to accept with two-third probability.
Right.
Right. And the same argument follows for the other case. So if x is not in L complement, that means that x is actually in L. By definition of BPP, we have that probability that M rejects x is at least two-thirds. So now what our new machine will do is our new machine will accept, sorry, rejects, this is accept. X is at least two-thirds. So that gives us our second condition, and we have a new machine M prime which satisfies this condition, and also it's pretty clear that it runs in polynomial time because M runs in polynomial time. After that, we are only deciding the flipping the accept reject. Okay.
Yes.
So okay, and similarly, yeah. So ZPP would be also the same idea, but you don't need to take care of this two-third probability and so on because it always gives you correct answer. So only flipping will do the job. We don't really need to show this.
Yes.
Okay, and it can also be shown that BPP is actually closed under union, um, yeah, union intersection and star operation, but we will not get into it right now. Okay, so yeah, so the next thing is before we solve this, so last time we had this discussion about Oracle Turing machine. So um, okay, so we had something like this. So a uh, some class, or let's say I'll call p for now, p to the sat. We had solved questions of this kind where we are giving an oracle access to a language, so you can assume that you have answers to that for free. That is how we define the Oracle Turing machines. And I think one thing I was not sure of last time was whether this can be a class. So you are right, it can actually be a class. So I can even talk about p to the np, and we need not. So when we say that np class is given as an oracle, we don't really mean that a complete language is given. Although in this case it doesn't matter, because if you give sat, you can assume that every other problem in I mean, you have access to every other problem in np. But for example, if I say p to the bpp does not have a notion of complete languages. So in fact, it can be shown that there are no complete languages. So we don't mean here that when we use say a complexity class here, we're talking about complete problems necessarily. What we mean is that you have access to every solution to every language in that class. So
So this thing is actually not clear to me. So instead of say P set, if we write P and P, then what would it mean?
that you have you if you give me any np language, you want me to solve it, I'll be able to tell you this. I mean, you don't really need to solve it. The oracle will tell you answer to any np problem.
Oh, okay. Yes. Yes.
But yeah, I'm saying in this case it does not matter whether you write sat or np, because you know that sat is complete for np. So if you want any language in np here, what you could do is you could use the cook-levin reduction and convert that into sat, and then now use the sat queries. So even if I don't give you np but I give you sat, you are still fine, because you can use the answers to sat to get your answers for n.
Yes. Yes.
Okay, but in case of BPP and so on, uh, we can't do that. So yeah, so we'll have to write the class.
Yes. It makes sense. Yeah.
Okay, so now this question asks you to show that the class BPP is low for itself, in the sense that even if you give an oracle access to it, it's as powerful as the BPP class without oracle access, and same for ZPP. Even if you give a ZPP oracle to it, it is as powerful as without oracle.
So it would mean that Oracle is not adding any
Hmm.
power to BPP. So if the string is a part of the language, uh, if the string is a part of the language, and I ask to the Oracle,
Hmm.
so the Oracle at the most will give me the answer with some probability
Hmm.
that okay, this string could be the part of the language, but with the probability of two-third.
Hmm.
But the element of the uncertainty would remain the same,
Hmm.
even if I have the access to the Oracle.
Hmm.
And that uncertainty factor, even that value, two-third or one-third, would also remain the same. So that would mean
Yeah.
that it is BPP, and same would be true for ZPP as well, I guess.
Hmm. Yeah, exactly. So the point is that when we ask oracle queries to BPP, let's say I want to ask whether say L is some BPP language, and I ask an oracle query, so it will tell me in order one time whether X is in L, but it will tell me correctly with probability two-thirds. So what you're saying is that actually I don't really need to run the oracle. What we'll do is, instead of this step, we will simply run the machine M for L, and it will run in P of an amount of time, but it will tell you the same thing. If it will tell you whether X is in the language correctly with two-third probability. So it's actually telling you the same answer. The only difference is in time. Oracle tells you instant, constant time answers, and uh, and if you run it, you are actually running in P of n time. But it doesn't really matter for us, because BPP is anyway, the decider for BPP is anyway a polynomial time machine. So even if I add a factor of polynomial more to it, it will still remain a polynomial. So, and therefore this BPP to the BPP is same as BPP, because you can as well simulate it. But the same argument will not hold if, for example, I change the base machine. So for if I make it less powerful, then the same thing will not hold. So for example, you can have languages such that A to the BPP is not the same as A.
I missed this point when you said that this A. So I mean, what is A complexity class is?
Um, I'm just saying it, if you take something less powerful, for example, say P,
Okay.
okay.
Yes. Yes.
Hmm.
Yes.
So in this case, it's
Right.
sort
Right.
of getting absorbed because the base machine was also BPP.
Yes. Right. Right. I understood this point. Yeah.
Yeah, and same argument actually goes for ZPP. Um, yeah, only that you really don't need to worry about the two-thirds probability, but yeah, same. It's actually the same argument, right? Hmm.
Yes.
And
Yes.
okay, so just one more thing that I want to mention at this point is that you saw two kinds of um, worlds. Okay, one was the deterministic world where you had P and P, and then you had polynomial hierarchy and so on. Okay, P space here. Okay, and the other side that we're seeing right now are this. You have ZPP, you have RP, co RP, and then you have BPP. Okay, so the question is, how does this world relate to this world? Like, I mean, do we know any containments on this side? So one thing that's like very obvious is that ZPP contains P, because It never says don't know. So in this case, what will happen is it will always tell you correctly, and the probability that it says don't know is actually zero. So yeah, so that is one containment that we know. We also know that RP is contained in NP, okay, and co-RP is contained in co-NP. Then we said we don't know what is this containment, what is this containment. mm, yeah, but if we want to compare BPP with these classes, then BPP is actually is in sigma 2 intersection pi 2, which is in this pH. Okay, and this is actually a very strong result. And yeah, so I think this was done in the class, right? So I'll not do the proof and so on, just want to show the picture at this point. And the other kinds of classes that are out there which we probably did not do and may not do are what are called counting classes. So for example, when you have this SAT question, it was a decision problem. In fact, all of these are decision problems at this point. Decision problem is whether fee is satisfiable. But you can actually think of a counting version of this. Counting version would be sharp SAT. How do we define that? Input is a fee and output is what is the number of satisfying assignments for fee. Okay. So yeah, so naturally if you can define classes like sharp p where there is a language is in sharp p, if there is a polynomial time Turing machine that will tell you this count in polynomial amount of time. And when we say tell you the count, what we mean is that there is a tape on which it will write the number in binary, and so it's a write only, you can't edit that, so it's not a work tape, but you have a separate output tape where it will write the count and leave it at that. So um okay. Okay, so okay, so is the definition clear?
Yes, definition is clear. So this a sharp set would be more difficult compared to the set, and sharp P would be difficult to the P.
Exactly,
And
yeah.
can this difficulty reach to the level wherein say it becomes somewhere equivalent to NP thing?
Equivalent to NP.
Yeah. So
Actually
like
it is,
can this sharp P reach to that level where it becomes as difficult as the NP problem is?
yeah, so actually the sharp is much more difficult than it seems. In fact, there was a theorem in 1998 due to Toda. It's called Toda's theorem. So um okay, so I don't, okay, let me just verify. So there is some deterministic machine here. So even if you give sharp p oracle access to it, it is contained in pH. So okay, I'll just check it once. Okay. This is p. Okay, so Okay, so this is actually a very strong result. In fact, it this this result won a Godel Prize to for Toda. It's actually a very strong statement, and the kind of tools and techniques that are involved in proving this are very non-trivial and very interesting. So you can look up it's a long proof, you can look up into it, but the only point that I want to mention here is that this is actually much harder than NP, not provably but intuitively.
Yes. And so when you write this pH as the intersection of the sigma 2 and then pi 2, uh, what would it mean?
Oh, sorry, so
What would
what
it
I
mean?
sorry, this part, right?
Yes, yes,
So I just
please.
meant that it is in the pH, that's I mean, so this is sigma 2 intersection pi 2, which is in pH, and this is in p space. That's
Yes, yes, yes. Yeah. By the way, what is the statement of the Toda's theorem, and what does it imply? And I mean, what is the interestingness in this result?
the interesting part is that so it kind of shows you how um, okay, so you only know that p is contained in pH, right? And what this sort of says is that
Yes,
even with access to uh, um, I mean, to this counting oracle, the class that you expect is still in pH. So okay, I really I mean, other than interpreting this, I don't know um, like how to motivate it further. But okay, I mean, I don't know at the moment. So I'm just reading out the statement. That's all.
yes, yes. Uh, yes. So this Sharpie stands above P, and uh, this is subset of the PH. No, no, no. Sharpie is not the subset of the PH. I mean, Sharpie stands somewhere here above the P, and difficulty level of Sharpie is definitely high. Yes, yes. This I understood. Yeah, yeah.
Oh,
All right. Yeah.
mm, okay. So yeah, we'll do one quick recall of one problem that we had seen earlier. So um, recall that the range avoidance problem is that you have, so this is, I mean, this is your single output circuit where, say, this is your output bit, and you can think of several circuits like that, taking, say, different subsets of inputs, and you can think of these as output bits. Okay, so, and these are your input bits. Okay, so this is nothing but a function from n bits to m bits. This is what is given as input to us. And the output that you want to give is a y, which is an m bit string, such that y is not in the image of c. That is, no matter what input we give, the circuit cannot produce that particular output. So this particular 0 1 assignment cannot be achieved no matter what inputs we give.
Yes.
Okay, so that's the question. So this is not a decision problem because I'm asking for an explicit y. Okay, so
Right.
okay, so um, okay, so then maybe I'll not call this ZPP, but I'll call this FZPP, where what we mean is instead of ZPP algorithm telling us whether to accept or not, think of it as giving us a value. So similar to what we had here. So although let's say we are not counting something, it's not really sharply analog, but think of it as writing something on the tape similar to this rather than just writing a 0 or 1. So that's the only difference. So otherwise everything in the other part of the definition remains the same. So you want to um, design an FZPP to the NP algorithm.
Yes, but yeah, uh, so I have access to the NP Oracle here.
Hmm.
And what is the difference you told about this ZPP and this F thing? If I had F here,
Huh.
uh,
So
what is that change?
if it were a ZPP algorithm, it can only tell whether to accept or reject. But with F stands for functional. So what this FZPP will do is it will write something on the output tape. So it has this. So for example, it can write a Y, an M-bit string Y.
Oh, okay, yes, 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 right. So now in this case, since I have access to the Oracle NP,
Hmm.
I need to formulate this problem into some decision problem so that I can yeah,
Hmm.
query to the NP Oracle.
Hmm.
And if I can, and then after asking to the NP Oracle, then I can write something there over the tape that okay, this is the thing.
Hmm.
So now I mean what could be that closest problem
Hmm.
in NP and which I mean to
Hmm.
which I can map this range avoidance.
Hmm. Hmm.
So if I give x1 to xn thing,
Hmm.
I need to ensure that I won't be getting say y1 as an output. I won't be getting y2 as an output.
Hmm.
So last time we saw in I mean last time you solved one problem that wherein a boolean so satisfiability could be that problem. And last time we saw that okay, so this boolean expression has exactly these many number of the solutions.
Hmm.
So yes. So then, if we can reduce this problem into that problem, that okay, does this problem has m number of the no, no, not m. I mean, I need to find the satisfiability. Yes, yes. I need to ensure that does this Boolean formula has m number of the solutions, and if the answer is yes, then I will ask, okay, so whether I mean, so then only then I need to, but then this y1, y2, all these are the, I mean, if I use the Boolean formula, I would be getting these values at the Booleans only. So all these values would be equals to one. Only thing I can ensure is that whether I have m number of the solutions or not. But how to see that the solutions are not there in this range? But then even in this case also y1 to ym, these all are the Boolean values only.
Hmm.
Since these are all Boolean values, so what would it mean that so basically, so y2, I mean, what would be the meaning of that? The value of y2 is 0. That for this given expression x1 till xn, this thing is not satisfiable or what?
Hmm.
I mean,
So what this
whichever
means?
x1 to xn I use, and I cannot get this y2 as the
Hmm.
output or what?
Hmm. So it is possible that, for example, you write a 0 here. It is possible that for some input assignment we get a 0 here. But maybe it's not simultaneously possible that we achieve this particular configuration all at once. So maybe this partial assignment is achievable by some inputs, but what happens is it's actually affecting the other functions also. So when we set some outputs, we are sort of imposing some constraints on the inputs. Because of that, I mean, it's leading to some constraints, and eventually we are not able to simultaneously achieve this particular configuration, although partially it may be possible.
Yes, yes. Now something is clear to me.
Hmm.
Uh,
So,
so how to I mean pose this problem as a decision problem
hmm,
so that I can query to the
hmm,
NP Oracle that I am unable to understand.
hmm.
Yeah.
So, um, I mean, so if we think of the oracle first, it will be slightly difficult to come up mm, with the idea. But if you think of the base machine, let's say the FZPP machine, then there is some randomness involved, right? So in the definition of ZPP, because there's some probability associated. So let's think of most natural random guess that we can think of. So let's say I give you one algorithm which says that randomly um, choose an embed string y. Okay, so this is the random guess that we have. And now, what is the probability that this y is not in the range of the circuit? So, can we analyze this? Because that is one thing that we need for ZPP, that we want to be sure with good enough probability.
Yes. Can you show this algorithm again? Yes.
Yeah, I
So
should
we
mention that.
randomly, yeah, that algorithm which you wrote below, I mean in the slide,
Sorry, yeah,
this algorithm,
yeah,
still it is not visible to me.
yeah, 1 second.
Yes, yes. Now it's visible. So we randomly select these values y1 till ym, and so that yes, yes. So then the ZPP will. So if I select this a binary string of the length m, so the ZPP will tell me that I mean for this particular configuration, is this the output? So then I mean ZPP will definitely tell me that whether this particular thing y1 till ym can be generated from this sequence or not. But then I'll have to query ZPP many a times. But yes, so
Okay, so
ZPP will always tell me right. Yeah. So how to take the help of the oracle then?
so to make sure whether buy is in the range or not, this is where we'll actually need the NP oracle. So how will it tell? So what will be a certificate? So input is a circuit C and a Y, and you have to say yes if Y is in the range, if and only if. So what is the certificate that Y is actually in the range? Sorry.
So the certificate would be uh, any binary string and excluding this y1 till ym. So if you give me that string excluding this y1 to ym, then that would be a certificate that yes, from this circuit I can generate this string, or I mean this string as the outcome.
If you give me some other string, how will I be convinced that it is in the range? That is, when we say it is in the range, there is some input setting that will uh, evaluate to that.
Oh, oh, I see. So this can be the circuit satisfiability problem, probably that I mean for a given string I would be getting. But then the circuit satisfiability, yes, yes, circuit satisfiability, but yes, uh,
Mm,
but then here there is not one circuit. Actually, this is the collection of the many circuits, I think.
hmm.
So yeah, so I'll have
The answer
to
is actually
yes.
much simpler than what you are thinking. Maybe that's why you are. It's actually. Mm, so,
So yeah,
so okay. So if you tell me x1 to xn, some values of x1 to xn, what I will do
so
is
if
I
I
will. Huh.
yes, so yeah, so if I have these values x1 to xn, then what that certificate be? So certificate would be that I mean whether I mean this set of the binary string. If I give you a certificate, a sequence of the zeros and the ones, it would be a valid certificate if it can be generated through these inputs x1 and xn.
Hmm. Hmm.
Uh,
Yeah. Exactly.
so
So if you give
so
me.
that's it.
Huh.
That's it. I
Hmm.
think.
Exactly. Yeah. So the certificate would be. a 0 1 value, the input setting. So what I'll do is, once you give me that certificate, I'll write x1 as 0 and so on based on the input, and I will evaluate the circuit. This can be done in polynomial time. So because you're just solving the circuit, the and or negation gates, and then you will evaluate this and see that okay, this is actually same as y, and therefore it is in the image of circuit. So
Right, right.
there is a small
Yes.
certificate for this. So this is where the NP oracle is helping us. The other thing that we want for ZPP is the probability that we should be correct with, uh, I mean, yeah. So, mm,
Yes, yes,
hmm.
yes. Right. And why this F thing is required here?
What is required?
F ZPP you said. I mean
Uh,
ZPP needs to be modified for something so that we can write something over the tape.
so we will write this y over the tape. So when once the oracle tells me that yes, this is not, I mean, in the no case that it is not achievable, we will output y, because y is the correct, y is what we want, right? Something that is not achievable.
Yes, yes.
So that's why
Yeah.
we have this f, but the only thing we need to analyze now is just probability, that a randomly chosen y is correct. What is the probability of that?
Yes.
So okay, so what we'll do is we will draw this figure that we have set of 0 1 to the m. These are all possible output bits, that output strings, but not all of them may be achievable, and these are all possible inputs. Okay, and notice that if I fix a certain value and evaluate it, I can only get one particular assignment. So one fixed input will give me one specific output, another input will give me another output. It is possible that two different inputs give the same output, right? But okay, so this is basically a function
Yes, yes.
image of C. So, and we are randomly choosing a y. So how many y's are good for us? So total number of y's is all possible m bit strings. This is 2 to the m. But the good ones, or let's say the bad y's, would be the ones that are in the range, because we actually want something outside. Okay. So what is a bound on this?
Uh, so, I mean, the lower bound would be that at least, I mean, nothing. I mean, we do not get so all zeros. Say, for example, that there is only one,
Hmm.
and I mean, this is not. I mean, nothing is satisfiable. So that
Yeah.
would be one.
And
And
what
the
is
upper bound would be
huh.
that, yeah, so all the values are achievable. That kind.
uh, so for one value here, you can only have one value here. So the worst case would be that all of them are distinct.
Yes,
So it could be, in the worst case, it could be the size of this left set.
that would be M.
Yeah, that would
N.
be n, 2 to the n.
Yes,
So
yes.
what is the probability that y is good? That is, y is
2
not
raised,
good.
yeah. So y is good means, so bad 1 minus 2 raised to the power n divided by 2 raised to the power n.
2 to the
Yeah,
power m.
that
And we know that
is
m is greater than n, then this probability is at least half.
right.
So if we repeat this process again and again, eventually you will get a y which is outside the range, and but we are running an expected polynomial time. So here we are using the second definition, that you will always answer correctly, but your runtime may be slightly worse than polynomial, but in expectation it will be polynomial time.
Yes.
Okay, so these are the three, what do you say, I mean, three aspects of it. One is that we use the NP oracle to actually check whether a randomly chosen y is correct or not, and the functional part is to write the y because we actually want y explicitly. And yeah, the third thing is that the ZPP argument, which is a counting argument that we are doing good with the with at least half probability. So
Yes.
okay, so now we will go to the circuits and do some quick recall. So okay, so one model of computation that we used throughout so far was the Turing machine model, where if I want to show that uh, whether L is in some class, we always came up with a Turing machine, whether it's deterministic or non deterministic, but it was a Turing machine model. So, for any language that we were interested in, we came up with a Turing machine for it. Okay, so another model that you can think of is what are called circuits. But circuits are different from the Turing machine in the sense that for a particular language L, you had only one machine description. But when you talk about circuits, we will talk about a family of circuits. So, for example, so if L is a subset of sigma star, you can think of it as union of L to the k, or I'll call it N for now. Okay. So now what we will do is for every Li here, so for L0, I will have some circuit C0. For L1, I'll have some circuit C1, and so on. So that finally I have actually a family of circuits which decide or accept L. Okay. So that is the only difference. Whereas in case of Turing machines, I don't need to give you separate machines for L equals 0, K equals 0, 1, and so on. There's just one machine that will take care of it. But for circuits, this is needed because when I give you a description of circuit, the number of inputs that it takes is already hardwired. So I can't
Uh,
change. Huh.
yeah, but then the Turing machine need not to be unique because the program need not to be unique for a problem.
True.
And
Yeah.
so, therefore, quite possible that I may take the union of the multiple Turing machines and something we may come up with something similar to the circuitry thing. Like say because we have a universal gate like say NAND kind of the thing, wherein I mean appearance wise quite possible that C2 may differ than C1, but then internally or I can always model this C2 in such a way that it becomes similar to the C1. Like say
So,
for the programs as well of like we have the Kolmogorov complexity kind of the thing, that I mean, for every program, we can find the smallest possible program kind of the thing. So one program can be modified in a way so that it becomes similar to the other one. So my point here is that instead of saying that for this L star we have a single Turing machine, it's okay that Turing machine will recognize clinic closure of L as well. But for the clinic closure of L, I can also have a union of the Turing machines. Like I can design a separate Turing machine for
right.
L2 and then L3.
But then what you are actually doing is that in that process, in the clean closure, what you're actually doing is you are internally running. So we are thinking of a machine M, which is let's say running M1, M2, and so on, all of them, and then based on their decisions, we are eventually going to decide whether now we should accept or not. So then we say that if either mi accepts, I mean, if any of mi's accept, then we will accept. So this machine is actually internally doing the same thing, that it's running them and then making a decision.
So does this mean that it's the circuitry C2 which is recognizing L2 cannot recognize L1? Is this the case?
Right, because when we say C2, it fixes the number of inputs to 2. Okay, when I
Oh,
talk
okay. Yes,
about,
now I
yeah,
understood. Yeah.
so there will be a different circuit for 2-bit inputs, 3 bits inputs, and so on. So
Yes,
this is
yes.
actually a, I mean, so Turing machine somewhat feels stronger in that sense that, mm, you don't need to define a family of machines. Although computationally they are equivalent, whatever you can compute by a Turing machine can be computed by a family of circuits, and vice versa. But this kind of gives you one single description, whereas for circuits you'll have to come up with a family. So yeah.
Yes, yes.
And how do we come up with these circuits? Well, we have this uh, Li. So Li is a subset of sigma to the I. Okay, so in fact you can think of this as a function. Okay, I'll just call it ln. We can think of this as a function 0 1 to the n to 0 1, where fn of x is equal to 1 if and only if x is in this language. So we are,
So this point is not that clear actually. So what is yeah, I mean how to view this thing as a function? Uh,
huh. So ln, this is a subset of 0 1 to the n, right? So sorry. Okay, so that means it has some strings. So let's say maybe it has uh, I'll call it, let me take n is equal to 3 for now, and let's say L3 is 1 1 1 0 0 1 1 1 0. So what is the function corresponding to that? um, whenever whenever this input is in this language, it will say 1. So here it will say 1. For 1 1 0 it will say 1. Everywhere else it will say 0.
yes,
So whenever x
clear.
is in that language, it the function says 1, otherwise it says 0.
Yes, yes.
Okay, so this is how you can think of, so this is actually the proof that for every Turing machine you can come up with a circuit, because what you do is, let's say L is the language that the Turing machine recognizes, or decides. We will break it into this union based on the length k. So you write it as L0 union L2 union and so on. For each Li, we will come up with a function, a Boolean function.
Yes.
Okay, and for that function, it's sufficient to show that there is a circuit Cn. So there is a circuit Cn computing Fn. So how do we do that?
And how to show this? Yeah.
Huh. So this is something that we already okay. So for this function Fn, there is a truth table like this on n variables and the values that it computes.
Yes.
So once we have the truth table, we can do the SOP, POS, I mean CNF, DNF thing. Um,
Yes.
so it uses and or negation gates, and we can come up with a circuit for it.
Right. Right. Yes.
Okay. So what this tells us is that if you only give me these three um, functions, and or and negation, I can compute any function. right? So in fact, you can even say that, let's say I don't give you the AND function, I'll only give you OR and the negation function. So in this circuit C, you're only allowed to use OR and negations. Even then, you can compute any function. So how will you show this?
What is to be shown? Uh,
Ha, okay, so I'll write it properly. So one thing that we said is that if you give me, so 2 here says that it's an OR of two inputs x1 and x2. Okay, so why is it enough? Because if it's an OR of k inputs x1 to xk, I can simulate it by computing several ORs.
yes, yes.
Okay, so it's sufficient to assume that you have an OR gate which with arity 2, you have an AND gate with arity 2, and a negation gate. So we saw that any function can be computed by a circuit with only AND, OR, and negation gates. So this is called a complete basis.
And what about the NAND thing? The NAND used to be the universal gate that
Exactly. So NAND is also enough. So if you don't give me any of these but only NAND gates, it is still a complete basis because I can simulate and using NAND gates. I can simulate OR and negation also using NAND gates.
yes.
Okay, so all these can be done. So this is also so this is one complete basis. This is another complete basis. Third thing is, let's say I only give you OR and negation. Is this a complete basis?
Uh, no, it won't be because then how would I simulate and kind of the thing here?
Hmm. So
So,
like earlier we showed that I mean we didn't show but we know that AND can be simulated by just NAND. So can you show that AND can be simulated by only using OR and negation?
and if I use the Morgan thing,
Hmm.
then x1 or x2 or x1 and x2 would be same as the complement of x1 or the complement of x2. So can we
Exactly.
achieve
So
it?
we will do De Morgan's law. So if you are computing G1 and G2, where G1, G2 are some functions, what we will now do is you will compute negation of or of, okay, or, so okay, we'll do negation of or of because G1, mm, yeah, this is same as G1 and G2 by De Morgan's law. Okay, so this is equivalent to computing this particular function, and then for G1 and G2 we will iteratively do the same thing. Okay, so this is also complete. So there are several, okay, some of these we already did, so we know that this is complete. Sorry, this is complete, this is complete. Now let's say you only have parity gates. So can we simulate and or negation all of them using just parity gates?
So there might be some equality showing that x1 XOR x2, because if both the values are same, then we are getting the output 1, else 0. Uh, and if what if I take the, but then only there is no negation, only XOR is given.
Hmm. But
If only
negation
XOR
can
is
be
given, then I mean, if
hmm. Then negation can be simulated because what I'll do is okay, if I do this, then whenever x is 0, it will output a 1, and whenever x is a 1, it will output a 0. So this is
yes.
basically
So
computing a negation.
oh, if it is performing the negation, then we can say that if I give 1 here, then I would be getting 1, and if I give a 0 here, if I give 1 here, I'm getting 0. If I'm getting 0, then uh, I'll get I'll get 1. Even though it is complement, but if I take 1, if I give 1 here, so 1 or 1, the value should be 1. It is giving 0. So I mean, I need to include some negation here. And if I use 0 here, then 0 or 1, the value has to be 1.
Hmm.
And this is giving me 1.
Hmm.
So I need to include something like, say, if the value of x is 1, but then
Hmm.
how to ensure this thing that the value, if this is 1, then use the negator, otherwise do not use negation. So that could be something like, say, in between these two circuit, in between x and this thing, I need to include some kind of the, uh, but how to, what do you mean, if else condition. So overall, I mean to say that yes, negation can be realized through the XOR,
Hmm.
but I'm looking for one more. Either I get an or I get an and,
Hmm.
which I can realize through this XOR so that it
Hmm.
becomes the complete system.
Hmm.
Uh, but I am unable to think that how to realize the or simple and from the XOR.
Hmm. So actually, yeah, I mean negations can be realized to XOR, but and as well as or cannot be simulated by XOR. So one uh, way to reason this is that uh, there's something called monotone function. So if, or let's say monotone circuit, let's say. So what is a monotone circuit? It only has or and gates. It does not have any negation gates. So and what is the idea here? The idea is that if, say, um yeah, so if it basically says that at some point in the circuit, if I'm starting to compute, let's say at this point, if I'm starting to compute a 1, and if I feed into okay, so I don't, okay, I'll not get into it, sorry, I'll take it back. um okay, it's simpler to define that in terms of function. So in terms of function, what it means is that at some point, if you started taking a value of 1, if the it cannot go down to 0 now. So it's something like it will keep going up, or it will stay at the same value, but there's no way that you can bring it down to 0. So that's so okay, maybe it's okay if, I mean, I didn't define it very properly, but I'll leave it for now. But the idea here is that parity, um okay, I'll draw the table, that would be easier. So this is a truth table for OR, um and I'll write parallelly for AND. Okay, so this is 0 1 1 1, and then you have 0 0 0 1. So what this actually means is that if I increase the number of ones, so this is what is happening. So initially you have 0 number of ones, then you have 2 ones, I mean one in each of them, and then you have two ones. So you're only increasing the number of ones. In that process, it cannot happen that if you increase the number of ones in the input, then your output goes from 1 to 0. It's only increasing. So from 0, once it switched to 1, it's only increasing. Similarly for AND, it was 0 initially, but once it saw two occurrences of 1, it took a value of 1, and it cannot go down from there. So this is intuitively what monotone means, although we will define this properly in the next lecture. But if you look at the truth table of OR, XOR, then the same behavior is not captured here. So what happens is it actually um, so it from 0 it increased to 1, but then you have more ones than earlier, but still the value is 0. So this is not a monotone function for that matter. So this is not a monotone function. So therefore you cannot simulate it using just and or gates. So this is something we will do next
Yes.
time. Okay, so yeah, I didn't go over the details, but you cannot actually simulate it with just and or gates. So that's, and we'll prove it properly next time, but that's intuitively the reason why you can't do it. So in fact, there is a set of rules that will tell you whether a set is um, complete basis or not. So by complete basis we mean if you just give those functions, you will be able to produce any compute any function that you want. So this is called posts um, characterization of complete basis. So there are several rules which if the set satisfies, then it is a complete basis. So S is, let's say, the set of functions that you are allowed. So if there exists a function in S such that f of 0 to the n is equal to 0, okay, it's not really if, but it should satisfy all of them, and there should exist another function g such that g of 0 to sorry g of 1 to the n is equal to 1, and it should contain a non-monotone function. Okay, so there are several of these rules. I'm not sure if these are the only three, but there are some four rules, I think. I'm not listing all of them, but if these rules are satisfied, then you are sure that it's a complete basis. So you don't need to go through the pain of always if you have some complex functions here, then we don't need to simulate everything using I mean and or negation using these gates. It's enough to check these.
So, so I mean, does this declaration of the basis has anything to do uh, with the with the operations required to write a program? Like I'm thinking to forget this into the duration. So I mean, does it have anything to do with that? Okay, I think many constructs are sufficient to develop any program, and not like say if the programming language is just complete kind of a thing. Uh, so that okay, the if is okay as if it has constructed is okay, and if it constructed okay, that that sense. So can these many constructs are sufficient to show that I mean all
uh,
other constructs are not actually
your
the
voice
programming
is
language.
coming a little muffled.
Yes, actually, I'm traveling, so this entire session I am attending while traveling. So
Oh,
there could be some network issue.
oh,
So
okay.
I have a question goes like this: that does this have anything to do with identifying the minimal construct for a programming language to be shown as to be complete kind of? I mean, that, okay, only these many constructs are sufficient in a programming language, and other constructs are not necessary. That's all. I mean, what
Okay,
is the relation between showing a complete basis from a programming perspective or from a
okay,
Turing machine perspective?
okay. So, Okay. So I'm not sure I understand it correctly, but what you're asking is how this is any. I mean, if it is related to uh, programming language, um, finding the minimal set of um, functions or functionalities that are needed or are sufficient to, I mean, have your program.
Yes, yes, yes.
So okay, I don't think this is directly correlated with it because okay, I'm not sure, but I don't think it is directly correlated because at the moment we are just looking for a specific functionality, which is that you want to have a circuit computing a particular function. Okay, okay, but okay, I mean, you could imagine any um, you could actually translate it into a Boolean function and then look for this. Is that what you're
Yes, yes, yes.
huh?
Because every algorithm
Interesting.
eventually
Okay.
within an
Mm-hmm.
is an encoded Boolean function.
Hmm. Hmm. But this is more like implementation, more on the implementation side. So once you have the Boolean function, it's just a matter of implementing. How do you want to implement it?
Yes.
Hmm. And hmm. Okay. So I okay, that is all I had. I mean, I don't know if I have yeah anything more to yeah add. Okay. So okay, so we saw that this is not complete. But what about if I add an AND gate to it?
Uh, so if I have because the knot can be simulated to this XOR, so
Hmm.
end and knot will give me the complete. So these
Exactly. So this is complete because now you have functionality of AND as well as negation, so you can simulate all. Also, one thing is that here we can look into the list of properties and see that we basically don't have any function in the set that satisfies the second requirement because XOR on all ones gave us a 0.
yes.
So that was violated, and so by invoking the characterization, you can directly say it's not complete. And what about the last one?
So what? So the last one is not complete because so we have negation only. Right?
Exactly.
Because it has
Huh. So this is not complete, and again you can again it's the same um, the requirement 2 that is violated. Okay. um, okay, so another thing that we'll talk about is, let's say I want to compute a parity of n bits. This is the function that I want to compute, but the gates that I have are only parity of 2. So how do we compute a circuit that finally I mean, how do we come up with a circuit that computes parity of n bits but only using these gates?
already using XOR. No point.
Yeah, so there are so one natural way would be that you think of this as um, parity of okay, so in terms of circuit, what that means is you first compute a parity of x1 x2, then you look at the result, compute a parity with x3, and keep on doing that, and eventually return the output. So how many parity gates did we use in this process?
So and, uh, for two, I would be requiring one. So on every level, we are using this one XOR. And since we are having I think n such students, so like two at a time. So uh, I mean, how many pairs are possible? So n to two number of the pairs are possible. So I would be requiring the n into n minus one by two number of the
Hmm. Okay, so in this case, we are not doing pairs, right? We are just doing serially. So first compute this, take its parity with x3, then look at the result and compute its parity with x4, and so on. So each time we're only, uh, I mean, like, so we are first computing this on the left, the value on the left hand side, then computing with x3, then you think of this as one whole value, compute with x4. So these are n minus 1 many operations. This is the first time that we computed, the second, and
yes.
okay, so these are n minus 1 gates. But if we look at the depth of the circuit, so how do we define the depth? From the root of the, or the output of the circuit, what is the longest path that we can take to an input value?
So that would be equals to n.
N. Exactly. So in this case, the depth is n. Now think of, this is just a point of view, that think of these as machines. So a parity 2 is one machine whose job is to take two inputs x1, x2 and compute its parity. Think of this as another machine whose job is to take these two inputs and compute the parity. So the uh, the question is, can these machines work parallelly? Because what happens is, the this machine depends on the first computation, for it to compute the parity of x1, x2, give me the output, and then it will take x3 and compute the output. So the same thing happens. So if I look at this, it cannot directly start working because it depends, it waits for this computation to happen. So it's a very serial um, way of computing, where this will start working only once this is finished, this will start working only once this is finished, and so on. So there is a lot of dependence. So if you think of this as parallelization, no, this cannot be a very parallelizable algorithm, and that is intuitively what depth is capturing. So when you say that the depth is n, what it means is you will have n many dependencies, or uh, some, so in that sense, so once this depth 1 computation is over, then you will do a depth 2 computation. Once this is over, you will do depth 3, and so on. So you want as less depth as possible, because that would mean that you have as low, as large parallelization as possible. Similarly, what this gates correspond to is how many machines I have. So ideally, I want as few machines as possible and as parallelizable as possible, because that will save time. So you can think of this as saving on time, and think of this as, so this is generally what we call the size of the circuit. We define it as the total number of gates that are there, and this sort of corresponds to the number of machines, or let's say space. I mean, it's not exactly space, but these are the two resources. So in the Turing machine world, I don't know where did we define. Yeah. So in the Turing machine model, the resources that we cared about were size, and time, sorry, space and time. Now in the circuit world, the resources that we care about generally are what are called the depth of the circuit and the size of the circuit, because depth somewhat translates to time, because that's how parallelly we can, how much in parallelizable the circuit is. And the size, roughly, it's not same as space, but it's somehow similar to it. Okay, so these are the two parameters, and ideally we want, so like earlier, you want as less time as possible, as less space as possible. Similarly, here you want the circuit to be as small as possible and as low depth as possible. Okay, so now if I want to compute the same function, but let's say I want to do it parallelize, I want to parallelize it. So now here we can use your idea, which was that I'll not compute it one by one. So what I'll do is I'll first compute x1 and x2. Parallelly, I will compute x3 and x4 and so on. So for now, assume that n is even. It doesn't matter otherwise also, but so in one step, I have um, all these parities at hand. Next, we will simply do mergings and keep on doing that. So eventually, you will get, yeah. So eventually, you will have computed the parity of n variables. But now we are doing it parallelly. So now, question is, what is the depth of it and what is the size of this? So let's do depth first.
So now, uh,
Sorry, I couldn't hear you.
yeah. So now in this case, we would be requiring that value, n square, the depth will increase. So
Hmm.
now for every OR gate, we require two inputs,
Hmm.
and everywhere we are required two inputs. So that would be of the order of n square. Will it be of the order of n square, the depth?
Mm, so
Depth,
by doing serially, we are using n depth, and now we are parallelizing it, so we can only hope it to be lesser than earlier,
yeah.
because
So that would mean that if I get a value one here, and so I, but then it's true that we can go for the parallel one, but then even though we are doing it parallelly,
hmm. Okay.
uh,
Hmm.
yeah, that's not clear actually.
Hmm. Okay, so mm, okay, so what's happening here is that at this point we are we are computing um, a parity of two functions. uh, I mean, so these are the two functions that we are computing, and at this point you would have split it further, right? So this is going to take, each of them is going to take two other end. So at this point you have four of them, and you're basically doing this 2 to the k function. So or if you talk about it reverse way, at this point you wanted a parity of n many of them, but here you have reduced them to half. So if this was n, here we have reduced it to n by 2 by combining two of them further each time.
Login kind of.
Exactly, so this is basically the log n. So it's a binary tree of log n depth. And what is the size of this? So how many parities we have used in this process?
Like so at the level 0 it is 1, at the level 1 it is 2, so 1 plus 2 plus so the size would include what? The number of the gates and the number of the inputs. everything
So inputs we
is
will leave away, only the gates.
only good, right? Then you will be requiring 1 plus 2 plus 2
N
square,
by
and
4.
you get that in till log n minus 1. So the many number of them should be for who knows, but then the size uh, won't be this thing because the size would be 1 plus 2 square if we are only counting the number of
Yeah.
the
So,
gates. So gates would be there 1 plus 2 plus 2 square and
so on
so
up
on.
to
They
N by.
made it 2 raised to the power log n minus 1 kind of. And this repeat
Or,
will came out to be 2 raised to the power of the order of 2 to the power log 2n, and that is of the order of n. So size would be of the order
size will be N,
of the order of n. N.
on the order of N, right? So this is order N. So what is really happening here is that we have parallelized the process by computing pairwise each time, and then combining them, keep on combining them all together. So that way we reduce this depth from N to log N, which is a pretty large improvement. But in that process we ended up using a lot of machines because we are doing so many computations parallelly. So yeah, each time. So earlier you only needed linear number of gates n minus 1, but now, okay, it's still okay. Maybe the constant here, okay, is it just n or is it something larger than that?
This is a GP, uh, GP value has to, there would be log to a number of n. So therefore the sum will be, yes, so the sum will be of the
Yeah. Yeah, so okay, so in this case it didn't so happen that we didn't really blow up on the size, but we achieved a better depth. Okay. Okay. So, but in other cases, it could happen that if you are trying to improve on the depth, you will compromise on the size and vice versa. So, like it was there in the case of Turing machines, that if you try to save on time, you may need more space, and if you want to save more space, then you may end up using more time. So, similar trade off is there between depth and size, and that will be something that we will explore in the upcoming sessions. There are couple of questions that were there on the circuit side, but we will discuss that next time. Okay. So I think I'll end the session there. So what we saw today was yeah, some review of this classes, BPP, RP, ZPP, and we saw how they are related with um, the other world of P and P space and so on. And we saw one or two examples where we are giving Oracle access to these classes and checking how powerful the class is. And then we did some basics of circuits. So yeah, so okay, next we will meet on Saturday, 10 a.m. to 12 p.m. again. So next would be again Saturday, 10 a.m. to 12 p.m., and we will discuss more about circuits.
Okay. Yeah.
Okay, so I'll end the recording. Thank you for attending.
Thank you so very much. Sorry for the bad